All right, so let's get started on this process of standardizing color. So I would like to sort of bring y'all up to this level. This is, I think, the trickiest analysis or spectral simulations that I've done is to convert Gaussian to visible spectra, which in its face is not tricky at all, but then you throw in the standardized color scheme, and then you're actually modeling the color of that molecule, which I think is really, really very neat. And so today we're just going to focus on that small piece of how we standardize color. So when you were taught your colors, that was just what we call a social convention, right? If you look at the spectrometer and you see the nanometers or whatever, they're not labeled red or green or blue. You know, those are labels we give them. And I even thought, just sort of to prove that this was a social convention, I thought about teaching my son that red was actually green and blue was actually yellow and all of that, but I thought, no, that'll totally screw him up. So, but you know, we could, like, I mean, in fact, y'all use different words than we do. We use English words for those colors. You use your words for that color. So, you know, the words are society-based. And that's no fun, right? So in terms, I mean, it is fun for culture and language, but it's no fun for science, right? Or even industry. So when I was in industry, we had specifications for accepting new material, right? And so you would get new material on the dock, and one of the specifications said that this yellow powder had to be the color of burnished gold. Because when it ages, it turns green. In fact, you saw it on that last talk, the silent talk. You know, it was yellow or green, and the green was old and had been exposed to light and so on. And so the acceptance of that yellow powder, that part of the criterion was burnished gold, that it had to be a burnished gold color. I had no idea what that was, right? And so there's a real problem. Do I reject or accept this material? And so the colors, the names of colors are a problem. If you ever go to like pick out paint with, you know, in the future, if you're ever, you know, married like I am and you go pick out a color, you know, this is seafoam green, you know. And that's different. Yeah, ecru. What is ecru, you know? And mother of pearl, you know. And all these names, you know, that doesn't mean anything to me, you know. Tell me the red, green, blue values. Give me RGB, okay? Now we can talk, okay? And so that's what I wanted to do, was to figure out how to standardize color, and it had already been done. In fact, it was done in 1931. So we're 90 years into this, and that so few. What?
And we still don't use it.
That's right. And there's still 90 years in, we still don't really teach it in our undergraduate curriculum or graduate curriculum, you know. And yet color is a big deal. You know, it's really interesting. So this is the process of standardizing color. So like methyl red is a dye. It's red to the eye, but this is our perception of color and our learned classification. We call it red, but it's not objective or quantitative. Now, it is objective in the sense that that's the property of the substance. So I would say that the color of that substance is objective. It's housed in the object, but the name red is housed in the subject that's making the evaluation. So there's the object and there's the subject. And if I'm making a subjective name like red, then it's subjective because you might use a different name. But the phenomenon of absorbing light is in the object. It's objective. It's mind independent. So if you measure it with the spectrometer and I measure it with a spectrometer, we'll get the same number. So it's mind independent. It's not dependent on your mind or mine, but it's in the object. So that's what we mean by objective. And so I wanted to get to an objective color measurements. And sure enough, there was this French International Commission on Color. And they said for color to be reproducible, you have to have a standard lighting, a standard evaluation of what color is that's objective, and a standard color space. So numbers that we can still give names to, but numbers that are associated with the different colors. So this is the purpose of this talk, is to learn about the perception of color, the science of color, and the technology of color. Then we're going to manipulate visible spectra to derive these things, these Tristimulus values. And so we're familiar with RGB values, right, from the computer age, but these are connected to XYZ, or Tristimulus values. So this originally was done with the Commission on Color, and they came up with these Tristimulus values. And so we're going to go through all of these things. I'm trying to teach you in this lecture how to do it because I want you to do it. So we're going to implement these things in a spreadsheet. And this one I'm going to hold your hand less on. I want you to be able to implement these equations and everything that we're going to do in this talk in the spreadsheet. Okay, yourselves.
This was my favorite lab in undergrad.
Okay, good. Well, see, the lab, you've got experimental data, and this will be simulated data from Gaussian. So we're adding more to that lab. So basically what you did in the lab with the experimental data, that experimental data will be pulled out and the computerized simulated data will go in. Okay. And so here's how we observe our color, transmitted color. You know, we're over here with our little eyeball. As an undergrad, when I first saw this on the board, I just thought that was brilliant, you know, to just draw an eyeball, right? It's like you stick your eye there, you see blue. What do you see? Okay, so that substance is blue because the light that goes through it is blue. If your eyeball is over here and you're looking at reflectance, okay, if this angle is preserved, okay, that's called specular reflectance. You see specular reflectance here? Do you know what I mean by preserved? You're looking right on the correct angle so that you're looking at the source. So you can look at your table. Maybe you can see in your table or your screen this screen. And so if this screen is being reflected off the table into your eye, you're at the correct angle. So you're looking at the direct reflection. If you're looking at any other angle, that's the diffuse reflectance. And so in this case, if our eye is down here, notice we're getting all other angles. It's going this direction, it's going in all these directions. And in fact, a lot of times we block this direction. So we'll put a stop there so that none of the specular reflectance can get out and get into our eye. It's only the diffuse reflectance. So this is, diffuse is all other thetas. Now there's a role for both of these. In fact, total reflectance is the sum of both of them. I'll just say diffuse reflectance best represents the color. Specular reflectance will tell you something about smoothness. And you can imagine that, like, does this tabletop reflect light as good as a piece of glass or a mirror, right? And so specular reflectance will tell you about how smooth the surface is. If you get a really beautiful image of the source, then you've got a nice smooth surface. If you have a matte finish and it's scattering light, then that's a diffuse reflectance. It's a rough surface. And so you can use specular reflectance to determine how rough or smooth the surface is. But also think about it. If I'm looking at that white light and I'm getting a really good reflection of the white light, I see white light. I don't see anything related to the object that I'm looking at. I'm looking at the source. So you lose color with specular reflectance, because if it completely reflects all of the wavelengths of the source, very little is absorbed. Even this black tabletop, it looks very white when I'm at the right angle with the lights up there. But at other angles, it's dark, it's black. And so at the diffuse angles, I'm getting the color of the object. At the specular angles, I'm getting the color of the source. I'm getting more of the wavelengths of the source. Okay, and so then we also have to have standards here. We put in a a blank or black object, a white object to give us our total illumination, sort of wavelengths, and then we put in our colored object. So we need to make 3 measurements for all of these, whereas transmittance, typically we can have a sample and a reference, a double beam spectrometer or something like that.
So something like a vacuum mirror has very little diffuse reflectance?
Yes.
So
Almost zero. Yes.
I was going to say, so like, does it not have its own color in a sense?
Well, no. So the glass is clear. It's transparent at all wavelengths. Okay. But if you had a colored glass, if you looked at the specular reflectance of colored glass, it would still appear colorless because you're looking at the source.
Right. Yeah.
Yeah. But you would just get off axis a little bit and you'd see the color of the glass. But if you narrow down just looking at the source, you're just going to be seeing whatever the source is. If this is a white source, you'll see a white and you won't see any color from that colored glass. Yeah. Now, be on the lookout for automobiles. Some of these, if I put, and this is off the lecture, I can't get sidetracked on this, okay? So if you put a thin layer here, okay, and you start getting interferences where maybe the red interferes, but the green has constructive interference at different angles, then you can have color changing paint that is angle dependent. There was a car in Huntsville. It was an HR. What is HR? What are those? What's the number that goes with those HR? Chevy HR 1 or something? Kind of looks like a hearse to me, but yeah. Anyway, there was one that was painted orange, but with this color changing paint, it went from orange to purple. Totally. I knew it wasn't just lighting, shadows, or whatever. I'm driving along and I see this car and it's purple, and as it got closer, it started turning orange. And I was like, nearly wrecked because because I've already zoned in on color, right? And I see that and I'm like, whoa, and then I saw it again and I saw it again. One time we were walking and it drove by and I said, stop. And it was like, what? And I was like, watch this car, and it went by. So I don't know. I haven't seen them in a long time. So maybe it was a student and they're gone, but there are some color changing paints. And I think they have a base coat and then they put a very thin, very uniform clear coat that's nano sized, like nano thickness. And so you're getting interference in the nano visible region, hundreds of nanometers that will play with the color.
So this all depends on what angle you're looking at?
All depends on what angle you're looking at. So it's an angle dependent filter.
Yeah, that's pretty cool.
It's very, very cool. So anyway, some things I geek out on. Wow, that's so great. And so then we have this Ocean Optics visible spectrometer that we use in the lab. And it just has a little holder. You put it on things and you can measure the color spectrum. And so you get this really, the visible spectra for these things are pretty boring. I mean, it's just like a cutoff filter, right? And so this is a reflectance spectrum. So it's reflecting the blue and the green and not reflecting the red. And so these are the transitions. Obviously, we have all these different n to pi star and pi to pi star and all those different kinds of transitions that are giving us absorptions in the visible region. And this is what we teach our freshmen. We have all of this available to us with the 90-year-old commission on color, and we still do the color wheel. Okay, if it absorbs in the yellow, it's going to, give you the corresponding or complementary color of violet. But this doesn't answer the question, what if there are 2 peaks? Okay. Right, and so yellow, like you got a 600 nanometer peak. That's lambda max. Okay, so that's great. That's a yellow absorption, but what's the width of that peak? Does it tail to the right? Does it tail to the left? And if you look at the papers that I have put up there for you on Blackboard, I show in one of the figures of that paper, it's a 550 nanometer transition, and it tails to the right, and it's a blue compound. If it tails to the left, it's a red compound. But it has the same lambda max. And so the thing is, lambda max is not good enough for telling what color it is. But yet we still kind of teach it that way. Like if it absorbs at, 550, that's the green-yellow region, it's going to be a red compound or a violet compound. And whether it tails to the right or left, if you have asymmetric peaks, like a log normal peak, it's totally different color. Even though the same center of that transition, but a different tail, right or left. So that's why the name of that paper is Beyond Lambda Max. Lambda max is not enough. We need to know the width of the peak. We need to know whether it tails to the right, tails to the left, to know what kind of color that substance is going to be. So here's a better color analysis than the color wheel. We take our visible spectrum. This happens to be the visible spectrum of permanganate. Okay, so you've seen potassium permanganate. This is what it looks like. This is transmittance, and so it gives some red here and some blue here. And you mix red and blue, you get purple. And that's what we've got. And that's what permanganate is, purple. Okay. When we run that through, that visible spectrum, we run it through this color analysis to determine the Tristimulus values, the XYZ. Then there's a matrix, the 3x3 matrix that converts XYZ to RGB. And then we convert those RGB values, which are roughly 0 to 1, and we convert them to 0 to 255. And then we type those into the computer. And so this is a box that I typed in these three numbers, and that's the color that I get from that spectrum. So that's really great. So this can be done with the visible spectrometer in the lab. Here's permanganate. It goes into the spectrometer and gives us that spectrum. But we could also add in computational chemistry. So that's what I'm doing with you guys. I did not do this with the undergraduates, so you're privileged in that respect. And so you get to do the electronic structure methods with Gaussian and create a spectrum and then run it through this analysis to get the color of the molecule. Okay. So let's go through these individually, these different pieces. Now this is, we want to have an objective system. And so that means we have to figure out how we perceive color. Now, do you know how we perceive color? I mean, we have a retina, right? It has rods and cones, and they contain certain pigments that are sensitive to color. So a photon comes in. A lot of times, I think maybe all the time, but I know for particularly the rhodopsin molecule, it's a cis-trans type thing with an azo group. And so light comes in and hits this molecule and goes from a bonding orbital that keeps these things planar to an antibonding and allows rotation. And so this photon excites like a pi to pi star transition, and then this ring is able to rotate. And just normal room temperature or body temperature vibrations causes that thing to start to spin, and it hits other molecules which create a signal. So light comes in, hits this pigment, we create a signal that's then interpreted in our brain as something of that wavelength has come into our eye. And so these just have different pigments in our eye. And for most people, there are 3. If you're missing one of those pigments, you're colorblind in some way. Okay. And I think that I've read, and again, I don't have I can't cite the source, but I think I've read that females have an extra pigment. It doesn't give an extra signal, but it gives more definition as to different shades in a particular area. So after I read that, I realized, okay, there's no real reason to argue with Jennifer over the differences in 2 colors. When she says they're different and I say they're not, this is not personality based, okay? She can see a difference that I can't. So that settles it, okay? And so it's science. That's right. It's not personality. I'm not being a pain in saying they're the same. They really are different, or they could be different. I don't know. I can't tell. She could be totally lying, but no, I don't think she is.
So women see more colors than men?
It's more like on the y-axis, more definition. I forget which pigment it is. I read an article 10 years ago. Is it purple? But it would be one of the blue or the reds. The red actually hits, if we'll notice, so these are the 3 pigments here. So how can we do this? How can we map out our eye without taking our eye out of our body? Because remember, we want to match the colors that we perceive. So we need to leave our computer in the mix. And I think this is brilliant, what they did. So how do you know when your eye is telling you that you're seeing a particular color? And this is how. So they have this 2-degree observer. So there's, in your field of view, they put these colors here to where, and I think it's the vertical axis, this is 2 degrees of your vision. Okay, so the center 2 degrees of your vision, so they know they're getting the right spot on the retina where you're going to have color, pigmentation, so you can see colors. And they have these 2 things. So they use a white light source and some sort of monochromator to send a particular wavelength here. So this might be, I don't know what wavelength purple would be, but let's just say 405. Why did I write a 2? So my brain is broken. Okay, 405. So they have 405 nanometer light going to the panel on the left. And then I'm the observer, and I've got 3 knobs. I've got a red knob, a green knob, and a blue knob. Okay? And so I turn up the red knob until it's too red, and I turn it back down. I turn up the green knob until it's too green, and I turn it back down, and I turn up the blue knob. What's going on is I am using my computer to tell them how much red, green, and blue light I need to match 405. And I'm using my computer to do it because I'm the one turning the knobs. Isn't that cool? Yeah. And so these are the knob settings right here. So I've got a whole lot of red knob and a lot, even more blue knob and no green knob. And then they scan the monochromator to another wavelength and they ask me to adjust the colors, and I adjust the colors. And what I'm doing is I'm mapping out my pigments. My pigments are what are giving me the signal, and then I'm taking that signal and turning it into the knobs. Isn't that cool? So I'm using my brain as the signal. Now they do this for lots of areas. This is color, but in the Panhandle, this big ag school, they wanted to know what compounds in the cattle industry smelled the worst. Okay, yeah, and so they had tryouts. And they had students come and they would smell different things, and they would adjust this dilution gas. So they would dilute it with, air or whatever. And so they would have parts per million of the smell going into this nose thing, and they would dilute it until it went away. And so they would turn up a diluent gas and the smell went away. And so they could map how good the person's nose was. Okay. And so you do this tryout. They try you on 3 or 4 different compounds, a thiol, an amine, stinky stuff. And you adjust these and like, okay, we got like 20 good noses here, And so then they had those students sit by a GC. All right. And they've got a thermal conductivity detector. Big old peak comes out, right? Goes into the nose piece. Student doesn't smell it. So that's not your compound. It's huge in this manure pit, okay? And you think the big ones are the ones that stink the most, but maybe not. Then the student's sitting there and this tiny little peak goes, whoop, and the student goes, oh, and turns up the dilution gas. And so if they just follow the dilution gas signal, they have the thermal conductivity GC, and then they have the olfactory GC. And then a really big peak. And so the tiny concentration had a big stink, and this one had a moderate and so on. And so we use our brains for detectors in different areas. And I thought that was brilliant. So this is the way they mapped out the they call them the observer functions. These are the observer functions, and this is how they map them out. And so here are our X, Y, and Z observer functions. And they are roughly RGB. The X is red. It's mostly in the red. The Y is G, mostly in the green, and the Z is the blue. So that's pretty cool, right? And Morgan's still trashed by this olfactory thing, I think.
What about a baby onesie with tiny concentration?
That's right. Yes. And then they could do white light too, and so they could map out your sources too. So this is how much light's coming through this white light source at all wavelengths. Okay. Now, this is how we also match like paints. So we can take these observer functions as in Excel, and we could fit them to any spectrum and get the XYZ values. And so we're saying if we have a spectrum like our permanganate spectrum that was like this, right? We would say, okay, our permanganate pretty much has no green in it at all, and has a lot of blue, and you know, it overlaps with the red about this much. And so it's got some red in it, a lot of blue, and that's what gives us our purple color. And so we're trying to see what our regular spectrum, how it matches these three observer functions, and that's where our three numbers come from, X, Y, and Z. Now, we could do this with different observer functions. We could do this with paint pigments, and that's what's going on at the hardware store. They have all of those pigments, like 150 of them or so, and they have all of their spectra, and you stick your paint color on the little spectrometer, and it takes a reflectance spectrum of it, standard illumination source, standard detection, and then it says what recipe best matches this. So they may have 100 recipes, and they pick the one with the best R squared, you know. And so they do the overlap of all of those pigment spectra with yours at various concentrations and the different base color and so on, and they can match it. And they can do this with your phone now. They have this little attachment that goes on your phone, and you can like stick it on your wall and then order the paint.
When
Isn't that crazy?
when I took your class, we were repainting inside of our house.
Yeah.
And when we picked the color paint we wanted, but the one we wanted was from a different manufacturer than their base paint was.
Yeah.
They said, well, we can't match that one. I was like, yes, we can. I have an Excel spreadsheet. And so I had them color it, and then we put their values into the spreadsheet.
Yeah.
And then did the correction based upon what the white was, the base was. And then, okay, I want you to program these RGB values in. And they
did it?
It came out correct.
That's crazy.
Like, I have a spreadsheet.
That's right. And the color lab. And so this is some crepe paper, like for parties, you know, the crepe paper that you have at parties. And this is the different colors. And I ran this analysis through. This is the ASTM E308. And so whenever you guys want to, you know, go update your resume, after doing this exercise, you can say that you know how to use ASTM E308. And you can put that on your resume. Okay, that's great. So color analysis. Okay, and so you typically get a raw spectrum. Look at the digital resolution here. I mean, it's, you know, it's sub-nanometer. And these observer functions were not determined at that high resolution. And so in ASTM E308, it's plus or minus 5 nanometers. So the digital resolution is every 5 nanometers. And these functions don't change that much. You know, they're very smooth functions, broad peaks. So that's plenty. You don't have to have sub-nanometer resolution. So we need to take this and break it into 5 nanometer digital resolution from 400 to 700 nanometers. So we take this and we do what's called a VLOOKUP. And so this is a new function for you if you're new to Excel, this VLOOKUP function. And so what it's going to do is it's going to go find, it's going to use this data here, this A3, and it's going to look in this table here, and it's going to come down until it finds 400. Okay, and then it's going to go over however many columns we tell it. We tell it to go over 2 columns. This is the table that it looks at. So it goes into that table, goes down and finds 400. When it finds 400, it returns column 2. And so then it returns that value that was next to 400. So this is like a database. It's searching the raw data for the particular wavelength that you want, and it's returning the transmission value. Okay?
If you were to put 1, does it just give you 400?
Yeah.
Right? As your...
If you were to put what?
If you were to put 1 instead of 2, it would just give you the number back 400?
Yes.
Okay.
Yeah, it's column 1. Mm-hmm. Yeah.
And what's the true false?
Okay, true is saying find an exact value, and the false would be if it's going up. Yeah, if for false it has to be a sorted list. And so if there was a 404 and a 406, I think it would return to 404. As soon as it goes over 400, no, I'm looking at 400. At 399 and say 401, you know, it would give the 399. So as soon as it gets above the 400, it stops and gives you the last value. This is how I check for emails and so on. Like if someone drops a class and I paste the grades in, and I screwed things up. So I have a sorted list of the emails, and I was like, first let's check the parity of my table and make sure nobody's dropped. And so VLOOKUP is really useful. But there I use a false because, no, I use a true still. I want an exact match to the email. I don't want the previous one. Okay, so here are the visible spectra of those different crepe papers. We have blue paper here. The colors didn't quite work out. So this is blue. Brown is this one down at the bottom. So that's brown. Green, this is colored green. Look how low that peak is in terms of reflectance. Only 20% reflecting, and yet that was a green, a pretty strong green paper. It was kind of like this. So a very bright color. And so our eye is super sensitive to green. It doesn't take much green reflectance for our eye to go, wow, that is bright. It's just super sensitive to green. So that's, a lot of times if you want something to be visible, contrast with green and it'll be visible.
Is that why there's a color shift sometimes from whenever people can misinterpret color from green to yellow? Because how sensitive?
It could be, yeah. So if that yellow, see, it's coming up with green here, but it adds in the red. But if you don't have the red, then you can really have a tough time distinguishing. So then this is the orange paper over here. It's blocking out this deep red, but it's letting this red. Let's see. No, this is reflectance. It's giving us red, and then this orange here. Let's see. Yeah, that's right. This is the orange, and this is the yellow right here. Yellow's giving us all the red, and this yellow here, and a little bit of the green. And then white paper is our standard, and so it's up here by definition 100% all the way across. So since we used it as our standard, it's a straight line across the top. Okay. And so we have these functions, and so what do we mean by fit? What are we fitting these functions? How do we fit functions? We use this, basically it's an integration, only it's in numerical integration. So we take this is our experimental spectrum. So this piece right here is R of lambda. And so that goes right there. And then this white line here is our intensity. So this is the S, or source. You're bored, huh? You're leaving. All right, and then this is the X, the red one in this case. And so this is just every data point in the R column times every data point in the S column times every data point in the X column added together. And that's real easy in Excel. It's just this sum product. Okay. So I have sum product, and I can select the columns of data. So this right here is 3 columns. And then we normalize it with the green. And so this is 2 columns of data down here. So does everybody see what we're doing? We're multiplying each individual data point and adding them all together, and that's an integral. And if there's a lot of X here, if there's a lot of X in our experimental spectrum, then this will be a big number, and it'll give us a big number for X. If there's a lot of Y of this function, so if our function overlaps with this green function here, then the Y value will be high. If I have a lot of zeros, see right here, I have a lot of zeros. So since my spectrum here is 0, and that's when green is high, I've got 0 times the green, and so I'm going to end up with a small Y value. So we're looking at the overlap of these functions, and if there's, zeros cancel out that overlap. And then this is the Z is the blue function. So this is key. This is the formula. These are the formulas you're going to put in Excel right here, sum product formulas. So and so those were put in here. It looks kind of long just because it has the names of the sheets on there. But this is sum product. This is the visible region for that one like permanganate spectrum. This is the color matching function sheet. and that's the source. So that's the illumination source, and then this is the X value color matching function. And then I divide by the sum product of the source times the green color matching function. And so that's the formula that will give me the X value for that particular substance. And then I copy that formula down and change that that third function to the Y function, and then copy it down and change that third function to the Z function. And then I've got my X, Y, and Z values. It's that easy.
The lab.
This is exactly the same lab, yeah. This piece.
Nightmares.
Yeah, okay. Now, if we take those, each X, Y, and Z and divide them by the sum of all three, this is called the chromaticity coordinates. And so this is a beautiful picture because you can see where this shows up. Like that red substance shows up in the red region, the green here. This is the permanganate, KMNO4, okay. And this is a nice figure too because it has the visible spectrum from 400 nanometers all the way around to 700 nanometers. And so I love the chromaticity diagram here, and it kind of shows you if you have something that's, 532, that neodymium YAG laser. It's that color green right there. Now, what David was talking about was this white point. You can adjust this white point based on your source, and so that can shift the whole system slightly. Here's how we transform from XYZ to RGB. So in '93, as personal computers and everything started to take off, there was an international color consortium that formed between big companies like Dell and Apple, HP, and so on. And what they wanted was a device-independent standard for color. When you think about it, they want to make sure that if I take a photograph and then I take that photograph and put it on my computer and I look at it through my monitor, it has an accurate representation of the color. And then what I see on my monitor, if I display it on a projector, you see what I see. And then if we print that off, then whoever's looking at the print sees what we saw, which was at the original spot. And it's not just about selling flowers and dresses. This is forensically important too. At the scene of the crime, right? It was a pink dress in the closet and the photographs show a yellow dress because the color wasn't accurately reproduced from computer to camera to print to screen and so on. And that kind of thing can happen. And so a lot of times we're trying to because I teach forensic chemistry, get them to put color cards in their photographs. Not just a number, not just a brightness, black and white, but to actually put color cards there so they can adjust the colors. And if they can adjust the color so that the objective standard is correct, then they know they haven't fiddled with the evidence, right? We don't care what the dress color is. We want to correct it so our color card is accurate. And then we have trust that something in the same photograph will also be accurate. And so this is just a 3x3 matrix. We have our X, Y, and Z values. We take this matrix, and we can do this in Excel, multiply this 3x3 matrix by this 1x3 or 3x1, and we get a 3x1 out, this RGB values.
Control shift enter.
Yep. And so this is our control shift enter, like you said, right there. So this is the formula here. So all these formulas are in your handout. This is how you do those formulas. And then adjusting to 8-bit RGB values, these values are roughly from 0 to 1. They can come out sort of negative here like this, or maybe if it's a really strong color, it might be 1.1 or something like that. So we just cap it. We say if it's less than 0, make it 0. If it's greater than 1, make it 1, or multiply it by 255. Yeah. If it's greater than 1, make it 255. If it's in between those two, then just multiply it by 255. And so we're taking this 0.6063, which is greater than 0 and less than 1, and we're multiplying that number by 255, and we get 16. Okay. And so this converts those standard RGB values into 8-bit RGB values, and then we can we could do gamma correction. We're running out of time. It's not that important, so we'll skip it. Then we can take those RGB values and we can create an object in Excel or in PowerPoint or in Word. We draw a square down here. Then we can click on more fill colors and go to custom, and we can type in those RGB values. And when we type in those RGB values, then we know what color that substance is. So this, from the beginning to the end, we can simulate the spectrum, generate the XYZ values and the RGB values, and we can see what color that substance is. If we had a photograph that we were going to compare to, then we could use ImageJS. I'll put this stuff in the notes just for your grins. It's really not a part of this project, but if you have a photograph, you could select this region and go to Tools and do a color histogram, and you could get the RGB values averaged of this whole area. And so that's pretty nice. Then you're not just picking a pixel, right? Because the pixels change, and if you want a representative area, this is what you would do, and it's really handy. If you got an image, you could type those image RGB values in here, and then you could compare them. And this is the typical match that we have. You know, this matches really well, and we've got 0:1672 and 0:2085. That's a pretty good match. So that's what we're talking about. We're not talking about plus or minus 1, but plus or minus 10 is good. Okay? And if you change that by 10, look and see if you can tell the difference, and you really can't. Maybe you could tell a difference. Jennifer could tell a difference, maybe. But you know, you have a pretty wide range of pigments in your response, and whether you say, yeah, that's a different color or not. In fact, they went through with their little observer people, and they changed the color, and they had them draw ellipses, or like they got lots of data on different people, and they could draw ellipses in that diagram to say, if it's within this ellipse, your computer is going to say it's the same color. If it's outside that ellipse, then you'll be able to discern the difference. And so they have this minimum discernibility ellipses around the different color spots. We have this phrase color gamut, and that gamut is the full range of colors that a system can display. And this is the RGB color gamut. So even though we've drawn all of these other colors here, the computer can't display them. The computer can only display the colors in this triangle. So that's the color gamut. And so sometimes when you're looking at a photograph and you say, it just doesn't do it justice, it's because it can't. The computer phosphors and your eye are different enough that they don't match. They don't have the same color gamut. And so we are limited in what we can do with this process, because the computer RGB color gamut only covers these. So, you know, from this point sort of straight out is the same color, even though you might fool yourself and say it can't be, you know, and from, you know, from this point straight out is the same color, because the computer cannot display a color different than the ones on that line, okay, and within that triangle. So and so these are the pure colors down here that the computer can display. And so this bright pink color is right there, and then the deep blue is right there, and then this, you know, cyan bright blue is right there, and the green and the yellow. You can see what's going on. So your eye is more sensitive than the computer is more flexible, I should say, than the computer. And this is somewhat of an approximation of what we can see with our eyes. The other thing that your eye has that the computer or a camera can't do, and that is, as far as we can tell, each individual cell in your eye has its own like preamplifier and sensitivity adjustment. And we have not made cameras that complex. So that's why a moon, you know, in the sky is so beautiful, because your eye can turn up the gain on the stars and everything like that, and turn down the gain on the moon and get everything just the right balance of brightness. But you try to take a picture with your camera, and if you turn down the gain so that the moon actually has some definition to it, everything else is totally black. You don't see the trees, you don't see the stars or anything like that. If you try to turn up the gain so you see the trees and so on, the moon is just a bright washed out area. I mean, you've tried this, I'm sure, with your phone. You're like, dang, it's such a beautiful moon, I can't get a picture of it, you know. And that's because your eye has individual amplifiers on each cell. Super complex, way more advanced than any camera element we've ever made. Well, I say maybe some scientist in some like NASA lab or something has made a camera element like that, but it's not on our phones and it's not in our Canon Rebel, you know, SLRs like I've got. Yeah. And so, you know, these notes have a lot of the tips for you for making this spreadsheet. And so it's going to take us a week to make this spreadsheet. So get on it. and next time we'll talk about some more of the details on the simulation side of things.